Good day. For those of you who do not know me, my name is Douglas Harder, and in this topic we're going to introduce this chapter on matrix decompositions. So in this topic we will begin by reviewing prime and polynomial factorizations. We will learn that the word decomposition is often synonymous with the word factorization. Therefore, we will introduce the concept of a matrix factorization, or more commonly called a matrix decomposition. We will describe 5 matrix decompositions that are useful in engineering, and we will identify those matrix compositions that we will see in this course. To begin, in secondary school you have already heard the word factorization. This is the process of breaking down a more complex structure into simpler structures. Another term for factorization sometimes is decomposing. Now, we are going to be discussing matrix decompositions, but this process is also known as matrix factorization. So again, in secondary school, you will have already learned 2 factorizations or decompositions. You know that every positive integer has a unique prime factorization. For example, 91 is 7 times 13, 1970 is 2 times 5 times 197, and this number happens to be equal to the product of these prime numbers. Now, actually, many public key crypto systems rely on the difficulty of factoring integers to send secure messages. So, for example, this very large composite number is actually the product of 2 very large prime numbers. Now, I found the larger number by finding 2 large prime numbers and multiplying them together, but going the other way, trying to find the prime factors of that larger prime is a very computationally expensive algorithm. Now, in secondary school, you also saw that all polynomials could be written as a factorization of either monic, linear, or quadratic polynomials multiplied by a scaling factor. Monic means that the leading term has a coefficient of 1. So, for example, here we have a 7th degree polynomial, and this can be written as this 3 times a product of 3 linear polynomials and 2 quadratic polynomials with real coefficients, where the 2 quadratic polynomials do not have real roots. In this course, we've actually taken it one step further and observed that every single polynomial has as many roots as there are degrees, and those roots may be either real or complex. So the above polynomial can be written as this: product of 3 times a product of 7 monomials, each of them representing one of the real or complex roots of the polynomial. Now, a matrix is a representation of a linear mapping or linear operator, and it is often very difficult to understand what it does. For example, one of these 2 matrices is invertible, that is, it has an inverse, or it has a determinant that is not equal to 0, whereas the other one has a determinant that is 0 and is therefore not invertible. Which one? Well, that's up to you to decide. You can try to figure that on your own. A factorization or a decomposition of a matrix tries to rewrite the matrix as a product of matrices that provides more useful information about the original matrix. Now, in this course, we will see 2, maybe 3 matrix decompositions. So in this chapter, we're only going to see one decomposition, and that's the PLU decomposition, although this is usually just called the LU decomposition. Later, we're going to see something called the eigenvalue decomposition or diagonalization. We may also see the singular value decomposition. Now, note that not all matrices will be able to be decomposed according to each algorithm. For example, the diagonalization decomposition, which we will see, actually only really truly applies to when a matrix equals its transpose. That is, each entry of a matrix that is not on the diagonal equals the entry of the matrix that is reflected through the diagonal. We'll look at some examples. However, in this introductory topic, we will actually describe 5 different decompositions: LU decomposition, the Cholesky decomposition, QR decomposition, diagonalization, and the singular value decomposition. Now, the PLU decomposition, which we will cover much more in detail in the next topic, basically says that every m by n matrix A can be written as a product A is equal to P times L times U, where P is an m by m permutation matrix. We just saw that. It's a matrix where every single column and every single row has exactly 1, 1. L is a lower triangular matrix that is square, m by m, and all the entries on the diagonal are 1. And U is an upper triangular m by n matrix. And if we do this correctly, U will actually simply be the matrix we get from performing Gaussian elimination. So, for example, here is a matrix on the left. It's not a square matrix, it's a rectangular matrix, but you will note that it can be written as the product of a permutation matrix times a lower triangular matrix with 1s on the diagonal times an upper triangular matrix. The Cholesky decomposition says that if we have an n by n square matrix where A equals its transpose, and the angle between U and A times U is less than 90 degrees for all vectors U, that is, the inner product between U and A times U is greater than 0, then that matrix A can actually be written simply as L times L transpose, where L is a lower triangular n by n square matrix where all the entries on the diagonal are non-zero positive real numbers. So, for example, on the left we have a square matrix that is where the matrix is equal to its transpose. So negative 0.06 in entry 1, 2 equals negative 0.06 in entry 2, 1. Similarly, entry 4, 3 and entry 3, 4, they're both equal to 0.54. And in this case, this is equal to the matrix L, which is lower triangular, times its transpose, where we flip all the entries below the diagonal to the corresponding entry above the diagonal. The QR decomposition says that every real m by n matrix can be written as a product of a matrix A times Q times R, where Q is an orthogonal square m by m matrix and R is an upper triangular or right triangular m by n matrix. So here's a simple example. On the left we have a 2 by 4 matrix, and it can be written as that rather simple orthogonal matrix. You will notice that both columns have a 2 norm equal to 1, and the two columns are orthogonal to each other. And on the right-hand side, we see an upper triangular matrix. Diagonalization. Diagonalization says that every real n by n matrix A, where A equals its transpose, can be written as U times D times the transpose of U, where U is an orthogonal n by n matrix, and D is a diagonal n by n matrix, where all the entries on the diagonal are real. So for example, here we have a 4 by 4 matrix where each entry above the diagonal equals its corresponding entry below the diagonal, so A equals its transpose, and you will see that this matrix is indeed equal to the matrix U on the left, where you will notice that each column has 2 norm 1, and all 4 columns are mutually orthogonal to each other. In the middle, we have a diagonal matrix that has 4 entries on the diagonal, negative 3.2, 0, 1.7, and 2.4. The matrix on the right is the transpose of the matrix on the left. Finally, the singular value decomposition says that every single m by n matrix can be written as a product of A times U times a matrix capital sigma times V transpose, where U is an orthogonal m by n m matrix, sigma is a diagonal m by n matrix where all the entries on the diagonal are real, and V is an orthogonal n by n matrix. Here's again an example. U is 2 by 2, sigma is 2 by 4, with entries 1.7 and 3.2 on the diagonal, and V is 4 by 4, and I've taken the transpose and shown it there. Now, it's important to understand that you don't have to memorize even the names of all the decompositions we just described here. Basically, for at least 2 of these, we were only describing them to make you aware that there are different decompositions that are sometimes useful in different circumstances in engineering. Now, in this chapter, we're actually only going to be looking at one decomposition, specifically the LU or PLU decomposition. It's only going to be in future topics that we will be looking at the eigenvalue and the singular value decompositions. So following this topic, you now have reviewed the decompositions or factorizations you've seen in high school, including prime and polynomial factorizations, and you are aware of 5 useful matrix decompositions or matrix factorizations that you may come across in the future. We've also introduced the 3 matrix decompositions that we will be seeing in this course. Here are the references, acknowledgements, the colophon, and a disclaimer. Cheers!